Okay, this may end up being a moderately difficult video. There are going to be a lot of weird things going on, a fair number of new words, but keep plugging. This video deals with isomers. Again, we talked about isomers in earlier videos. Isomers are molecules with the same formula, but different attachments. Another way of saying this is isomers are molecules with the same formula, but different IUPAC names. This is butane. This is called 2-methylpropane. They have the same formula. They are both C4H10, but they are not the same molecule, so they are isomers of each other. There is a different kind of isomer. We also talked about cis and trans isomers in a previous video. Well, believe it or not, there's an even different kind of isomer, and this one is really weird. It is called a stereoisomer. There's a definition. I took this definition from an old version of your book. It says the stereoisomers are molecules where the atoms are bonded in the same sequence, but differ in the way they are arranged in space. That doesn't make any sense to me. It may not make any sense to you. So to explain what a stereoisomer is, I have a thought exercise, and here it is. You look at these two gloves, and you can pause the video and think about this. Are those gloves identical to each other? On pausing the video, what I'm going to tell you is the answer is no. They are not the same. They are not identical to each other. There's a left glove and there's a right glove. And if you have ever tried to put your right hand in a left-handed glove, or the other way around, it doesn't fit quite right. And because putting your left hand in a right-handed glove doesn't fit quite right, that means that the left glove and the right glove are not the same thing. They look an awful lot alike, but they're not the same thing. Same with your left and right hands. Your left hand and right hand look the same, but they're not the same thing. In chemistry, one thing that you say about them is they are non-identical mirror images of each other. And the important part here is the non-identical part. What I mean by mirror image is if I take a mirror and put it like that, the reflection of this glove will be the other glove. So there are mirror images of each other that are not the same thing, the same way that these gloves are non-identical mirror images. In chemistry, what you would say is these gloves are stereoisomers. What do I mean by stereoisomer? Well, there's a left one and a right one. The left one is a stereoisomer of the right one, and the right one is a stereoisomer of the left one. There's our first weird word. They are mirror images of each other, but not only that, they are non-identical mirror images of each other. They are not the same thing. And here comes a new word. In chemistry, what you say is those gloves have a chiral feature. This is a really weird word, and it takes a little bit of getting used to what it really means. What chiral means is there's something about this glove that makes it a left-handed glove. And there's something about this glove that makes it a right-handed glove, or whatever. There's something about it that makes it left or right-handed. That's what chiral means. So who cares? Who cares about stereoisomers? Well, it turns out that there are a lot of molecules that also have chiral features. In other words, there are a lot of molecules out there in the world that come either in a left-handed form or a right-handed form. Another way of saying that is some molecules out there in the world can be non-identical mirror images of each other. It turns out that this is really important in biology and medicine, and I will explain that in the next video. So here's an example of two molecules that are stereoisomers of each other. There's a carbon here, that's a carbon. Right there, that's a carbon. And you can see this molecule over here, it has a hydrogen, chlorine, iodine, bromine stuck to that carbon. If you look over at this molecule, carbon in the middle, hydrogen, bromine, iodine, chlorine stuck to the carbon in the middle as well. You can see that they are mirror images of each other. Here's the mirror. The chlorines are pointing toward each other. The hydrogens are pointing up. The bromines are pointing away. The iodines are pointing down. So this molecule here and this molecule here, they are mirror images of each other. What I'm going to tell you is they are not the same molecule. And this is something that I would have doubted when I was a beginning student. I would have said, look, those two things look exactly the same. They're the same thing. But there's a test that you can do to show that they're not the same thing. And it's not so easy to do in a video. If we were on ground, I could show you this and it would be a little more convincing. But the test is this. If these things were identical to each other, then I should be able to turn this one. I should be able to spin this one around so that all of the different colors point the same way as are pointing here at the same time. But if you take this one and you spin it, and that's what they're trying to do here, if you take this one and you spin it around, you can never get all of the colors to point the same way at the same time. So they've spun the left one around. You can see the H's are pointing in the same direction, the iodines are pointing in the same direction, but the green and the brown atoms, they're not pointing in the same direction. And there is absolutely no way that you can turn this molecule and get all 4 colors to point the same way at the same time. It just won't work. At some level, you're going to have to take my word for it. And the fact that you can't do that means that these two things are not the same. Because if you could do that, if you could spin this one and get all the colors to point the same way at the same time, then they would be the same. But I'm telling you, you can't do it. So these things, although they look an awful lot alike, they are not the same. And they are called stereoisomers of each other. If you want to think of this one as like a left hand and this one as a right hand, you can do that. So there are some molecules that are non-identical mirror images of each other. This carbon in the middle here, the carbon that's in the middle in both cases, it has a special name. It is called a chiral carbon atom. Sometimes it's called a chiral center. So there's something special about this carbon that makes it so that this molecule and this molecule have a left or right-handed feature. And that's why it's called a chiral carbon or a chiral center. Now I'll explain what it is that makes those carbons special in a few minutes, but we're starting out and I'm just telling you this is called a chiral carbon. And just to confuse the matter, I'm going to draw another 2 molecules. There's molecule 1, here's molecule 2, and they are mirror images of each other. The H's are pointing toward each other, the bromines are pointing away, the chlorines are pointing up and down. So these molecules are mirror images of each other. But what I'm going to tell you, just to upset everybody, is that these 2 molecules, this one here and this one here, they are mirror images of each other, but they are identical. They are the same thing. So how is it possible that I'm showing you 2 molecules up here, they're mirror images, and I'm telling you they're not the same? And I'm showing you these 2 molecules, and I say they're mirror images, but they are the same. What is different about them? You can pause the video and think about that for a minute. Not the easiest thing. Unpausing the video, it has to do with this carbon here. This carbon has 4 different things attached. Not just 4 things. They're all different from each other. There's a hydrogen, a chlorine, an iodine, and a bromine. Hydrogen, bromine, iodine, chlorine. If your carbon atom has 4 different things attached, they have to be different, then your carbon will be a chiral carbon, and your molecules will be stereoisomers of each other as long as you have mirror images. But down here, we don't have 4 different things attached. We have 4 things attached, but they're not different. There's bromine, there's hydrogen, and then the chlorines are identical to each other. So there are only 3 different things attached here. Only 3 different things attached here. So the thing that gives you a stereoisomer with organic molecules is you have to have 4 different things attached to a carbon in the center. And that's shown on the next slide. If the carbon is bonded to 4 different things, it will have a mirror image that's not identical to itself. And that's shown here. If it doesn't have 4 different things, if it has fewer than 4 different things, it'll have a mirror image, but the mirror images will be identical to each other. Another thing that I want to point out. Oh, so just in case you're wondering, I could show you a molecule on a quiz or a test, and I could say, does this molecule have a stereoisomer? And what you're supposed to do is you're supposed to look at this and say, does this carbon have 4 different things attached? In this case, the answer is no, because there's 2 hydrogens attached there, and they're the same thing. So if I said, does this molecule have a stereoisomer? You'd say no, because the central carbon is not chiral. Another thing that I want to point out to you here is you can see that these molecules have a 3-dimensional shape, and this H is supposed to be pointing toward you in 3D. The iodine is supposed to be pointing toward you in 3D. Bromines and chlorines are supposed to be pointing away from you. It's hard to draw these things on a flat surface and make them look 3-dimensional. I mean, obviously, whoever did this did a very nice job, but chemists usually don't have that level of skill. So there is a way that chemists show people where the atoms are pointing in 3D, and it's shown here. If you draw a tapered bond and you fill it in completely, then whatever is at the end of that tapered bond is pointing toward you in 3D. If you draw a tapered bond and you draw dashes, then whatever is at the end of those dashes is pointing away from you. So if you see that type of writing, that is just chemistry's way of showing you which atoms are pointing toward you and which atoms are pointing away from you. So you may see that in upcoming videos. I know you saw it at the end of one of the videos from last week, but I said that we weren't going to cover it yet. Well, now we are covering it. Here's a little bit of a punchline. All organic molecules have mirror images, but there are two kinds of mirror image molecules. If you have a molecule with 4 different things attached to a central carbon, then the mirror images will not be identical. These molecules are non-identical mirror images. They are stereoisomers. If you have a molecule with fewer than 4 different things attached to the central carbon, then the mirror images will be identical. So these two molecules are mirror images, but they are not stereoisomers because they are the same molecule. Now you can ask, why are you talking about this forever, right? Why am I talking about anything forever? Probably no good reason, but a couple of reasons. One is that looks can be deceiving. If you showed me this as a beginning student, I would have said they're the same thing, but they're not. They're not the same thing. The other reason why it's important is that other than water, you and I are mostly made of water molecules. The most important molecules in your body are organic molecules that are chiral. In other words, the organic molecules in your body come either in left-handed forms or right-handed forms, but usually not both. And that's really weird, and I'm going to explain why that's weird and important. This is a sugar molecule. It is called D-glucose. This is also a sugar molecule. It is called L-glucose. You can probably take a look at them and see that they are mirror images of each other. And they are non-identical mirror images. This molecule and this molecule, they're sugar molecules, but they're not the same. They're stereoisomers. So who cares about that? Well, the one on the left here, if you eat this one, it will taste sweet to you, and you can get calories from it. You can use it for food. This one over here, if you eat it, it tastes sweet, but you can't use it for food. You can't get any calories from it. The reason is that there are molecules in your body that are designed to break this molecule apart. And you can think of this molecule as being like a left hand, and the molecules in your body that break this apart are like left-handed gloves. And so this molecule fits into the left-handed glove, and that the molecule in your body breaks it apart. It turns out the weird thing is your body does not make any right-handed gloves. So you can eat this, but it won't fit into the left-handed glove molecule that breaks this one apart. This one will just pass through your body, and you won't get any calories from it. The weird thing that I'm trying to point out here is that your body makes a whole bunch of organic molecules, and many of them your body could make left and right-handed versions. But usually it will only make one or the other for every particular type of molecule that your body will make. In other words, if there's a molecule in your body that's responsible for breaking this down, well, your body only makes the left-handed glove or the left-handed molecule that's responsible for breaking this down, and it never makes the other kind of molecule. This is like if you had a factory making gloves and the factory only made left-handed gloves or right-handed gloves, but not both. But that is what our bodies do, believe it or not. There's another example of this. Oh, one thing you can say is, what could you possibly use this molecule for? Tastes sweet, can't be used for food. Well, you could use it as a no-calorie sweetener. We don't use this as a no or low-calorie sweetener. The reason we don't is because this is too expensive to make. It costs too much money compared to other low-calorie sweeteners, but you could if you wanted to. So your body can tell the difference between left and right-handed molecules because your body mostly either makes only left-handed or right-handed molecules and not both for specific jobs. Here's another example. This is your stomach, right? The interior of your stomach is acidic. And there are little molecular pumps. There are little molecular pumps that line your stomach, and these pumps pump little H pluses into the interior of your stomach. And those pumps are called proton pumps because H plus is basically a proton. And those proton pumps pump H pluses into the interior of your stomach to make it acidic. But sometimes those pumps can go a little crazy, and they can pump too many H pluses, and some of those H pluses bubble up into your esophagus, and you end up feeling heartburn. Now, one of the things that you can take to deal with your heartburn is a medicine called Prilosec. There it is. And some of the molecules in Prilosec, after you eat them, they will break apart and they will go to the pumps and they will shut off the pumps. And if you shut off the pumps, or if you shut off enough of them and you wait long enough, then the H pluses will wash out of your system and your heartburn will go away. So that's what Prilosec does. And Prilosec is called a proton pump inhibitor because it shuts off these pumps and gets rid of your heartburn. If you look at the molecules in Prilosec, there are two of them. This is number 1, this is number 2. And hopefully you can see that they are mirror images of each other. And they are non-identical mirror images of each other, so these things are stereoisomers. Turns out that this bottom molecule here, even though it's in the Prilosec pill, doesn't do anything. This is the only one that shuts off the pumps. The reason is the same thing as what I described before. You can think of this as like a left hand, and this molecule is like a right hand. But the pumps are only made as left-handed gloves. There are no right-handed glove pumps made, and so this is the only one that actually shuts off the pump. This one just doesn't do anything. Now, there's another example of stereoisomers in biology and medicine, but there's a little bit of business here too. What chemists have done is they have made other pills that only have the top molecule and throw the bottom molecule away. And they resell those other pills that only have this stereoisomer in them. They resell them as Nexium. So Nexium is another drug used to treat heartburn, but it's basically Prilosec, but with this molecule thrown out. And then they charge you probably 10 times as much for the Nexium. And, maybe some of the marketing is, oh, you only need to take half as much Nexium to have the same effect as Prilosec. Well, that's because half of the Prilosec molecules really aren't doing anything. There's another word that I want you to know, and it's enantiomer. I am not going to go into any detail about this, but I just want you to know that this word is approximately equal to, that's what this little squiggly thing here means. Enantiomer basically means the same thing as stereoisomer. There is a subtle difference between the two of them, but as far as we are concerned, if I say enantiomer, you're going to say, oh, that means non-identical mirror images. It means stereoisomer. This Prilosec and Nexium story, it is not the only story of medicines with stereoisomer molecules in them. There's a whole part of the pharmaceutical industry devoted to this. There is a drug called Celexa. I think it is an antidepressant, and it has 2 stereoisomers in it. One of them is effective for treating depression, the other one is not. And then there's another drug called Lexapro, and that is basically Celexa with the useless stereoisomer thrown away. There's Ritalin, which is used for ADD. That has 2 stereoisomers. One works, the other doesn't. And then there's Focalin, which is Ritalin with the junk thrown out. Prilosec and Nexium are the same. There's a drug called Ventolin, which I believe is used to treat asthma. This has 2 stereoisomers. Xopenex is the same thing as Ventolin, but with the junk thrown out. So there are many examples of this in medicine. So what do I want you to know? If I show you a simple molecule, you should be able to tell me if it has a stereoisomer or not. And what you're going to do is you're going to look at the carbon in the middle, and you're going to say, are there 4 different things attached to that carbon? If there are, then it has stereoisomers. You should know what chiral means. Chiral just means there's something about the molecule, or there's something about something that makes it have a left-handed or right-handed feature. You should know what stereoisomer or enantiomer mean. And you should know why enantiomers are important in medicine. And that's the end of this video. The next couple of videos will deal with carbohydrates, and then thankfully we are done.
Well, it's over and over. Oh, oh no, oh, oh no, I'm gonna ride on the winning time. Well, it's over and over. Oh, oh no, oh no, I'm gonna ride on the winning time. Brother Noah, my God's talking, said he would ride on the wind and tide. Hey, children, stop, still, and listen to me. God walked down to the briny sea. He declared that the evil to send for man, and then he decided to destroy the land. He spoke to Noah. Noah stopped. He said, Noah, I want you to build me an ark. I want you to build it 3 cubits long. I want you to build it big and strong. I want it 30 high and 50 wide, so it will stand the wind and tide. It's oh Noah, oh Noah. Oh no, I got to go to ride on the wind and time. Well, it's a oh, no, oh, no, oh, no, I got to go to ride on the wailing tide. Got to go to ride on the wailing tide. Got to go to ride on the wailing tide.
Oh, Noah, brother Noah, my God's talking. Said he would ride on the wind and tide. Well, after the foundation was laid, then Noah began to hew and build. The ringing of the hammer cried judgment, the hewing of the saw cried sin repent. 100 years he hammered and sawed, building the ark by the grace of God. When the ark was done, God's voice was heard. He said, now Noah, let me tell you what to do. Calling the animals 2 by 2, so he called them in the ark 2 by 2. He called the birds the ox with the kangaroo. Then he called and Japheth, the ham and Shem. Then God began to flood the land. He raised his hands to heaven on high, shook the stars and moon from the sky, shook the mountain, he troubled the sea, hit the wind to his chariot wheel. He stepped on land, stood on the shore, and he clapped that time. There wouldn't be no more.